am Wang Shao from School of Computer Science and Technology, Wuhan University of Science and Technology. The topic of this report is Consistency-Constancy by knowledge learning for pedestrian detection in night surveillance. Co-authors include Wang Zheng from Wuhan University, Liu Wu from GDAI Research Institute, Xu Xin from Wuhan University of Science and Technology, Chen Jing from Wuhan University, and Lin Jiawen from National Tsinghua University. Pedestrian detection, aiming at locating pedestrians in images, is a key technology in the security field. The task of pedestrian detection is to determine whether there are pedestrians in the image. If there are pedestrians in the image, the position information of the pedestrian are given, as shown in the images on the right. This is important for tracking, identification, and behavior analysis. Existing research shows that there are big differences between pedestrian detection in daytime scenes and night scenes, which are mainly manifested in four aspects. In terms of the average number of persons in the image, there are more persons in the daytime scene and fewer persons in the night scene. In terms of light distribution, the light of the daytime scene image is brighter, but it is darker at night. In terms of performance, the performance of the daytime scene is higher, but the performance of the night scene is worse. At the emergency level, pedestrian detection in daytime scenes is more mature, and pedestrian detection in night scenes is more urgent. A straightforward solution to this specific problem is to enhance the image and perform downstream detection tasks. It is difficult to make these two tasks fit each other, due to diverse targets and constraints. Besides, image enhancement requires pixel-to-pixel image pairs for low light and normal light to learn the degradation and constraint relationships between them. It is difficult to obtain such image pairs in surveillance scenarios. Another option is to use as much labeled data as possible for the detectors. In the actual surveillance, each camera captures a large amount of video data, and there are discrepancies between different scenes. It is not possible to annotate all pedestrians obtained by each camera in practice. Noteworthy, surveillance device has its unique characteristics of working day and night and 24-hour. It is easy to obtain the images of daytime and nighttime from the surveillance. It is reasonable to use the knowledge of the same surveillance scene in the daytime and nighttime to assess the pedestrian detection at night. For the characteristic of working day and night and 24-hour, it is easy to obtain the images of daytime and nighttime from the surveillance. It is reasonable to use the knowledge of the same surveillance scene in the daytime and nighttime. For the consistency knowledge, DI and NI are the pedestrian distribution for day and night surveillance, respectively. It can be seen that the values on the diagonal are hidden inside the confusion matrices between the two distributions. The distributions of pedestrians in the same scene during the day and night are consistency. We named this phenomenon as distribution cross-time consistency. For the constancy knowledge, the cameras of night surveillance are most fixed. The background of different frames in the same camera is constancy, and the background of the night surveillance can be obtained. Based on the background, it is feasible to extract the foreground, which includes almost all pedestrians. The foreground can help detectors to obtain pedestrians, especially for pedestrians who lack color and texture information due to the low illumination and low contrast. We named this phenomenon as background cross-frame constancy. This is the framework of our method. The consistency knowledge module is used to explore the incentive effect of high-confidence detection results in daytime surveillance scenes on pedestrian detection at night. The consistency knowledge module is used to learn the auxiliary role of foreground images in pedestrian detection at night. The bi-knowledge representation promotes the consistency and constancy knowledge between the two modules and merges the final results in the best combination method. For the consistency knowledge module, this module is mainly used to combine the original pedestrian candidate proposals and the distribution of pedestrians in surveillance. During training, the correspondence between the ground truth and the predicted pedestrian position needs to be established. This branch is constrained by positional regress laws. For the constancy knowledge module, it combines RPN and FF to generate pedestrian candidate proposals. The additional information is background. In the foreground extraction, the block-level background initialization technique has been selected for the free-flowing surveillance conditions. The progressive strategy has been introduced for initializing background for the balls. For the bi-knowledge representation, although both consistency knowledge module and constancy knowledge module are useful for pedestrian detection for night surveillance, direct concatenation does not produce satisfactory results under complex conditions. We use the idea of mutual learning from each other to integrate the two branches. It contains two constraints, KL and LBI in the whole integrated process. We choose night surveillance data set to verify the proposed method, mainly because this data set is close to the actual military scene distribution. It is collected from actual surveillance data, spanning from 7 o'clock in the evening to 5 o'clock in the next day, covering nearly 38K images and 52 key pedestrian bounding boxes. The resolution of the image is 1920 multiplied 1018. The data set has covered two common weathers, sunny and rainy days. Similar to existing datasets, the attributes of the night surveillance have been classified into several groups to allow more fine-grained evaluation using different settings, scale, small, medium, large, light, low, medium, high, occlusion, rainy, and blur, etc. Compared with the baseline, the consistency knowledge module achieves optimization of 1.57 point MR, which demonstrates the effectiveness of the pedestrian distribution in the daytime scene for the pedestrian detection in night surveillance, as shown in Table 1. The consistency knowledge module achieves optimization of 3.21% MR, which demonstrates the effectiveness of the background for the pedestrian detection in night surveillance. Similarly, the 1.6% improvement of CCVL over the direct fusion demonstrates the effectiveness of the proposed bi-knowledge representation module. The main reason is that the direct connection strategy treats the two modules equally and does not comprehensively analyze and mine the optimal combination. However, the bi-knowledge representation module has done sufficient analysis and interactive learning from the consistency knowledge and constancy knowledge modules. Moreover, it makes an adaptive combination optimization of both modules at the future level. For different subsets of scales, the MR was reduced by 0.81%, 1.6%, and 3.95% on larger, medium, and small scales representatively. The performance optimization is inversely proportional to the scale size. Small scales are hard to distinguish for detectors, and the proposed method shows better performance for small-scale performance with the help of pedestrian distribution prior knowledge of surveillance. For different subsets of lights, the MR was reduced by 2.79%, 1.83%, and 3.44% on high, medium, and low light, respectively. The performance optimization is more obvious in high and low light. Exposure and low light are difficult elements for the detectors to distinguish pedestrians from the background, while the proposed CCBL draws on the distributional prior and background prior knowledge in surveillance. For other subsets, the MR was reduced by 2.67%, 3.7%, and 4.8% on occlusion, ring, and blur situation, respectively. The performance optimization is more prominent in the blur subset. The contours of pedestrians in low-quality, blurry images are not clear, while the proposed CCBL forms on the by-knowledge representation of prior knowledge of pedestrian distribution and foreground. We compare the proposed CCBL with several state-of-the-art methods on the night surveillance pedestrian detection dataset. Figure 4 shows the quantitative comparisons on the test set. Concretely, we achieved the MR of 18.69%. The performance of our proposed CCBL outperforms other existing detectors. The main reason is that the method proposed in this paper makes full use of the surveillance scene's characteristics and refines. From the visualization, it can be seen that the existing method shows better performance when the pedestrian is close to the camera or when the light is normal. The effectiveness of existing methods is unsatisfactory when pedestrians are in difficult situations, such as dark places or small scales. However, the CCBL in this paper utilizes the distribution of pedestrians and the background prior. The distribution of pedestrians can provide the probability of pedestrian location, and the background information can assist in the extraction of foregrounds, which contain pedestrian areas in very difficult regions. Meanwhile, we found that a small number of difficult samples were neglected in the annotation of night surveillance dataset, especially pedestrians with dark clothes in dark, as shown in the last two images. We have validated the proposed CCBL with existing methods on the night scenes dataset. Competitive performance is achieved in different scenes. In crowded scenes, such as squares and sports scenes, CCBL distinguishes pedestrians from the background well. It mainly lies in the fact that the pedestrians in such scenes are far away from the camera and accompanied by the generation of occlusion. CCBL uses a prior distribution and background, which has some discriminative power for extracting such samples. If you have any questions or suggestions about this paper, please contact me as soon as possible. I hope we can continue to explore